So we're going to talk about average and instantaneous rate of change. We're going to specifically focus on this function, which is maybe distance relative to time. Maybe you're kicking a ball, something like that. The ball is modeled by this function here, which is essentially a parabola. It's a positive function. It's an even one. So heading upwards, okay? Let's say we want to find the average rate of change between the times of, maybe 0 and 2, okay? Which essentially would be our t or x values in this case. Okay. Now, an average rate of change, if we were to graph this function like we talked about, I'll give us a rough graph here. That's the wrong one. Let's see. There it is. Oops, open. That's not what I wanted. Sorry. Here we go. Let me set this guy up. Okay. So if we were to graph this guy, he essentially has the shape of something like this. Okay, it's a pretty steep parabola. Okay, so it's taking off. If we're looking for the average rate of change between 0 and 2, we're looking for the rate of change from here and some value way up here. Okay, now average rate of change is essentially, when doing it this way, is we're finding the slope between those 2 points. So when those 2 points would cross. And now obviously this isn't perfect, but it's considered a secant, so a line that crosses through and ends up way up there, okay? And it's probably much, much higher than what we've estimated here. So we're looking for the slope, and we know slope, we've done slope before. We know slope is equal to y2 minus y1 over x2 minus x1. Now, they'll represent it by saying the change in y, that's what this stands for, a triangle, change in y over the change in x. Okay, well in our case, x is our time and distance is our height, we'll say. So what we're going to do is find the changes in our y's and divide it by the changes in our x's using this formula. So I'm going to give myself a little room here. We'll talk about the change in y and the change in x, and then we'll solve for the change in y divided by the change in x. Okay, so here's our 5t squared. Well, the change in y. Well, the first one was when our x value was 0, right? We're talking about 0 and 2 in this case. So we have to actually plug in 0 and 2 for here. So we have to find f, so this is f at x. We need to find f at 0 and f at 2. Okay. Well, f at 0, when I plug it in, is going to be what value?
0.
0, that's right. F at 2, 2 squared is 4 times 5? 20. Okay. So let's call this our y2 and our y1. Okay, let's keep that in mind. Well, in that case, we do 20 minus 0 gives us 20. So the change in y is 20. So in other words, our number on top will be 20. Change in x, okay? Well, our x value, where are the x values we were talking about? And this is our x2 and our x1, right? So we're looking at the value of 2, subtract 0, which gives us 2. So our change in x is 2. So the change in y over the change in x is actually equal to 10. So let's say that was the distance. It looks like it was changing at maybe 10 meters a second between there. Okay? So that was our average rate of change. Okay? And that's essentially how you find average rate of change. You find the differences between the y values, x values, and divide them. The way they want you to learn instantaneous rate of change is the exact same way in terms of a formula, but instead, if we're looking for instantaneous rate of change, let's say we're looking for the rate of change at the value of 1 here, when x is 1. Okay? I'll tell you the x is 1, I know the y value is technically 5 for this function. What we're going to do is we want to find a value extremely, extremely close to it. So doing the same idea, we'll kind of set it up the same way in our chart. The only difference being here is with our f at x, our x values are going to be a little different. I'm going to choose the x values of 5, and the other, so that'll be our x1, let's say, and our x2, that's going to be like 5.0001, something like that. Or it could be like 4.9999, whatever we like, okay? So we plug these values in. So first we need to find f at 5. And f at 5 is 25 times 5, I think it's 125. This one we'll need a calculator for, because the decimals actually become very important to us. So squared times 5 is, oh, I messed that up. Let's do that again. 5.0001 squared. Oh, I think I hit divided, that's why. Times 5. We'll just go to 0.005. Okay? So 125.005. Okay, that's good. So this is technically our y1. Okay, because this was our x1 value, this will be our y1 value, this will be our y2 value. And we already know that, if we were to subtract these, sorry, we don't already know that. If we were to subtract these, y2, subtract y1, that'll give us our change. So that's 125.005, subtract 125. What's that going to give us?
0.00.
So our change in y in this case is 0.005. And then our x changes. Well, that's technically 5.0001, subtract 5, which gives us a value of 0.0001. So our changes in our x are 0.0001. So our instantaneous rate of change, we take these two values and we divide. So 0.005, is it only two zeros? We're pretty sure?
Yep.
Yeah, okay. Divided by 0.1230 gives us 50. Okay, which is a pretty good estimate. And that's probably really accurate. So the instantaneous rate of change, around 5, we were talking about at the value of 5, we had to choose a value that was extremely close, is about 50 meters a second. So it's changing at 50 meters a second at that point, at this specific point. So we looked at one specific point where average rate of change is between two specific points.